Salam alaikum. My name is Velimir. I am instrument engineer trainer from Croatia. Having a great oil and gas experience, I decided to prepare a presentation of fundamental notions of instrumentation. I consider essential to get basic knowledge of instrumentation. With this knowledge, it will be very easy to every instrument technician to understand instrumentation and perform his duties. This presentation is useful not only to instrumentation people, but to all professions. Shukran. The first topic of presentation, fundamental notions of instrumentation, is instrumentation basics. It answers the questions: what is instrumentation, what is measurement, how it works, what is control loop, how it works, what is control system, what is distributor control system, and what is its architecture. The second topic of this presentation speaks about International System of Units, SI, which is the system of measurement used officially in all countries except USA, Myanmar and Liberia. It has 7 basic units from which all other units are derived. And precisely for length the meter, for mass the kilogram, for time the second, for electric current the ampere, for thermodynamic temperature the Kelvin, for luminous intensity the candela, for amount of substance the mole. The great advantage of SI system compared to imperial system is that bigger units are obtained from base units by multiples of 10 and smaller units by submultiples of 10. For example, unit of mass is kilogram. A bigger unit ton is obtained by multiplying kilogram by 1000. A smaller unit gram is obtained by multiplying kilogram by 0,001. For length, unit is meter. A bigger unit, kilometer, is obtained multiplying meter by 1000. A smaller unit, millimeter, is obtained multiplying meter by 0,001. In imperial system, 12 inches is 1 foot, 3 feet is 1 yard, and 1,760 yards is 1 mile. So bigger or smaller units are hardly obtained from base unit. My strong suggestion is to use only SIE system and not to mix it with imperial system. Unfortunately, everybody mixes the two systems, and this creates confusion and may lead to errors, accidents and disasters. The most famous are when a Canadian aircraft was loaded with cubic feet instead of cubic meters and remained without fuel in the sky. Fortunately, the pilot glided to the nearest airfield. And the second famous accident is when NASA lost a spacecraft supposed to land on Mars because one contractor used SI system for calculation and the other imperial, and this led to mismatch and crash of the spacecraft on Mars surface. So once again, do not mix the SI and imperial systems. Do not use PSI, millimeters or inches of water for pressure. Use Pascal or bar. Do not use cubic feet, use cubic meters for volume. there is a big misconception in the use of kilogram in SIE system. SIE system has a kilogram as a base unit of mass, not of weight. Unit of weight is Newton. Unfortunately, this is not accepted in everyday use, and everybody uses kilogram as weight, and this is wrong. So if you do not want to use weight expressed in newtons, use mass expressed in kilograms. The third topic describes the documentation necessary for operation and maintenance of a process plant, with the accent on instrumentation, and represents my unique contribution to make operation and maintenance understandable, affordable, and safe. There are 10 types of documentation in a process plant or project. Hazardous area, which shows hazardous zones in a plant. Process description describes the process. Block diagram is a schematic illustration of a major process units. Process flow diagram shows the relationships between the major components of a process unit. Piping and instrumentation diagram is a schematic illustration of functional relationship of piping, instrumentation, and system equipment components. Layout is the disposition of all equipment and instruments. Instrumentation index is the list of all instruments. Datasheet contains all data of an instrument. Loop diagram shows all electric or pneumatic connections of an instrument. At the end of this topic, I have put a brief description of symbols used in various process diagrams, especially in piping and instrumentation and loop diagrams, because every technician or engineer must be able to read these diagrams. The fourth topic deals with explosion protection of instrumentation. An explosion is defined as a reaction of explosive matter, solid, liquid or gas, and oxygen in air, initiated by fire in form of spark or heat. Explosion generates fire and pressure. Fire has no pressure, and absence of pressure distinguishes it from explosion. In process plants, there are only explosive gases that can cause an explosion. Hazardous area is an area where atmosphere contains explosive or flammable concentrations of gases. For an explosion, 3 components are necessary: explosive gas, oxygen, and explosion source in the form of spark or heat. There are 3 main methods of explosion protection of instrumentation. The first and most used is prevention, which prevents instruments to produce an energy which can cause an explosion. It is called intrinsically safe protection. The second method contains the explosion in an enclosure. It allows explosion to occur in the enclosure without propagation outside. It is called explosion-proof or flame-proof protection. The third method segregates instruments from surrounding atmosphere containing explosive gases. Usually it is realized by putting instrument enclosure under slightly higher than surrounding atmospheric pressure. It is used in analyzer shelters. Gases can explode only between minimum and maximum concentration in air, called respectively low explosion and upper explosion limit. If the concentration is below lower explosion limit, the gas will only burn. If the concentration is above upper explosion limit, the gas will not burn or explode. It is very important to know that a spark can cause a gas explosion only if it has a minimum explosion energy. Regarding minimum explosion energy from spark, there are three groups of gases. A, with minimum explosion energy of 180 microjoules, B, with minimum explosion energy of 60 microjoules, and C, with minimum explosion energy of 20 microjoules. Gases from group C are more dangerous than gases from group A. Regarding minimum gas explosion temperature, there are 6 temperature classes from T1 to T6. T1 is the highest and T6 the lowest explosion temperatures. Gases with lower explosion temperatures are more dangerous than gases with higher explosion temperatures. Gas with low explosion energy due to spark can have a high explosion temperature. It means it can easily explode by spark, but not so easily by temperature. Hydrogen has a very low explosion energy from spark, but very high explosion temperature. Hydrogen belongs to group of gases C and is very dangerous regarding spark energy, but is little dangerous regarding explosion temperature, as it needs high temperature to explode, and belongs to temperature class T1. The fifth topic deals with measurement accuracy, and it is my special contribution for an easy explanation of a very important topic, usually not understandable and wrongly interpreted. Measurement accuracy is the level of exactness of measurement. Measurement accuracy, or simply accuracy, is the opposite of measurement error. It is impossible to achieve error-free measurement. There is always an inaccuracy or error in every measurement. A measurement error is always present. There are 3 definitions of measurement errors and one of instrument class. Absolute error is the difference between exact measure and effective or actual measure taken by person who carries out measurement. Absolute error is expressed in measurement units, for example in units of flow, pressure, temperature or level. For example, a pressure gauge with scale of 1 to 10 bar has, for example, absolute error of 0,1 bar. Relative error is absolute error divided by effective measure. Relative error has no units of measure. Relative error of the above mentioned pressure gauge with absolute error of 0,1 bar has relative error at 5 bar or half scale of 0,2 and at 10 bar at the end of scale of 0,1. That is 1/2 of relative error at the middle of scale. It can be seen from relative error definition that relative error is big if effective measurement is small. Every instrument has a measurement range or measurement scale. The measurement must never take place at the beginning of scale when measuring small and therefore relative error big. Percentage error is relative error multiplied by 100. Percentage error is almost always used to express the measurement error of an instrument. Percentage error must be always referred at which part of measurement range or scale is taken. For example, percentage error of 1% must be referred, for example, to the end of range or scale. Instrument class is absolute error expressed as percentage of instrument range. Pressure gauge of range 0 to 1 to 10 bar in class 1 means that its absolute error is 1% of 10 bar, that is 0,1 bar. As a sixth topic, I have put a very important suggestion regarding safety of pressure gauges. Pressure gauges have generally a Bourdon tube as pressure sensor. Bourdon tube can leak and fill pressure gauge enclosure with process fluid, which pressure will in that case expel the plastic tab protection situated on the rear of pressure gauge enclosure. But this protection can fail, and in this case the glass in front of pressure gauge can explode and kill the observer. There are certified pressure gauges with explosion-proof enclosure. They are 25% more expensive, which is negligible compared to acquired safety. I strongly suggest to order new pressure gauges and to replace existing pressure gauges with explosion-proof enclosure. Fundamental notions of instrumentation. Presentation summary. Instrumentation basics, international system of units, documentation, explosion protection of instrumentation, measurement error, pressure gauges. Introduction to instrumentation. What is instrumentation? Before defining instrumentation, let us speak first about process plant. Process plant is a factory where raw material, for example oil, is treated to produce gasoline, liquefied petroleum gas, diesel, etc. Process plant or any company consists of people, money, information, and production. Production consists of mechanics, civil, electrical, process, and instrumentation. Mechanics are vessels, pumps, compressors, pipes, hand valves, check valves, and eventually safety valves. Civil are buildings and pipe rack. Pipe rack is the construction which supports the pipes. Electrical part consists of high voltage power supply 100 kilovolts, substation to transform high voltage into medium 6 kilovolt and low 0,4 kilovolt voltage, electric motors and heaters. Process is a procedure how to produce a product from raw material, as for example refinery process, LNG process, and so on. Instrumentation. Instrumentation is the science of measurement, control, and analysis. Measurement is the comparison between measured physical quantity, for example length, and its unit of measure, meter for length. The length of this table is 2 meters. This means 2 times 1 meter. 1 meter is the unit of length. The measurement of a physical quantity takes place by means of a sensor or detector. Sensor transforms a physical quantity into an electrical or pneumatic signal sent to transmitter. Transmitter transforms this signal into a standard electrical or pneumatic signal suitable for transmission. Sensor transforms a physical quantity into an electric signal utilizing a physical property. For example, change in temperature changes the resistance of a platinum probe. Platinum probe is in an electric circuit, and its change of resistance changes a current which is measured, and the change of current is proportional to change in temperature. Platinum sensor. Temperature sensors and transmitters. All instruments function in this manner. Instrumentation consists of transmitters, controllers, and control valves. These three elements, transmitter, controller, and control valve, constitute control loop. We see below left in blue transmitter from my Algerian French presentation transmitter, up power supply, alimentation in French, up on the right controller, régulateur in French, and below red control valve, van de réglage in French. This picture is a real picture of three elements of control loop with addition of a picture of personal computer, as the information of elements of control loop as measure signal, controller set point, and controller output are visualized on the monitor of personal computer. The set of elements of measure, control, and analysis constitute the system of measurement, control, and analysis. Previous systems had field instrumentation and a control room for each process unit. There was no central control room. Modern systems have a central control room for all units. Let us see the difference. The classic and most used distributed control system is constituted of field instrumentation on the bottom of picture, junction boxes, multi-cables, and two cabinets, one with intrinsically safe isolators and the other with input-output modules and controllers, and workstations with monitors. The classic distributed control system is in reality a centralized control system. Single cables to junction box and multi-cables from junction box to cabinet with isolators are blue because they are in intrinsically safe circuit. The real DCS has controllers in the field, avoiding multi-cables, and two cabinets, and has a communication network to access workstations. It is a real distributed control system with controllers in the field in small control rooms of every unit without personnel. Operators are situated in a central control room connected with field instrumentation and controllers by Ethernet network. In case of failure of Ethernet network, plant continues to be operated from the field without interruption. This is the picture of centralized control room with monitors, with keyboards, duplicate screens on the wall, and in the middle hard-wired emergency shutdown switches. International System of Units SI is world's most used system of measurement. International System of Units is used officially in all countries except in the USA, Myanmar, former Burma, and Liberia. It has 7 basic units from which all other units are derived, and they are currently: for length, the meter; for mass, the kilogram; for time, the second; for electric current, the ampere; for thermodynamic temperature, the Kelvin; for luminous intensity, the candela; for amount of substance, the mole. In this picture, we see base quantities, names of their units, units symbols, and quantities symbols. Unit symbols are normal vertical letters, and quantities symbols are inclined italic letters. All formulas indicating quantities must be written with italic letters. Note that symbol for unit of length is vertical M, and symbol for quantity of mass is inclined also M. All other units are derived from base units. There are 22 derived units. In instrumentation, we meet only two base units, level and temperature, and two derived units, flow and pressure. Measurement is comparison between the value of process quantity and its unit. For example, the pressure of 5 bar is the comparison between the value of pressure 5 bar with its unit of 1 bar. Pressure of 5 bar means the pressure is 5 times greater than the unit of pressure 1 bar. Greater or smaller units are obtained from base units by their multiplication by multiples or submultiples of 10. Multiples of 10 are obtained multiplying 10 by 10 on the power of 1, or 10 on the power of 2, or 10 on the power of 3, and so on, and submultiples by dividing 10 by 10 on the power of 1, or 10 on the power of 2, or 10 on the power of 3, and so on. For example, the base unit of pressure is Pascal. The greater unit is bar, equaling 100,000, or 10 on the power of 5 Pascal. 100,000 is multiple of 10, obtained multiplying 10 by 10 on the power of 4. For example, the base unit of mass is kilogram. 1,000 times smaller unit is gram, which is 1 kilogram multiplied by 0,001, and 0,001 is submultiple of 10. This is the reason why SI system of units is very easy to use compared to imperial system of units. I suggest to use only SI system for measurement and not imperial system. Using both systems, which is common practice, creates confusion, difficulties, and leads to accidents. In two videos at the end of this topic, there are shown the two most known accidents due to simultaneous use of both systems. Force is one of 22 derived units. It is defined by the second Newton's law. Force is mass by acceleration. Acceleration is speed divided time. Therefore, force is mass by speed divided time. Speed is length divided time. Therefore, force is mass by length divided time on the power of 2. And therefore, unit of force is kilogram by meter divided second on the power of 2. Unit of force is called Newton N. Let us learn another derived unit. Work or energy is force by length. Unit of work is joule. Joule is Newton by meter. Power is work divided by time. The unit of power is watt. Watt is joule divided second. We can thus express joule as joule equals watt multiplied second, or work is power by time. Let us learn another derived unit. If we raise the length to the power of 2, we get the area. The unit of area is 1 square meter. Pressure is force divided area. Unit of pressure is Pascal, and it is the force of 1 Newton applied to the area of 1 square meter. Pressure is the quantity very much used in instrumentation. Pascal is a very small unit of pressure, so practically a 100,000 times greater unit is used, and it is called bar. 1 bar equals 100,000 Pascal. In instrumentation, further than pressure, 3 more quantities are used, and they are temperature, flow, and level. Temperature is one of 7 base quantities of SI system of measuring units. The unit of temperature is Kelvin. For practical use, another unit is used called Celsius. Celsius is Kelvin minus 273,16. Flow or flow rate is the volume or mass passing through a certain section in a unit of time. Flow is expressed in kilograms per second or liters per second or their multiples. Level is the height of a liquid in a container. It is measured in meters or percentage of a maximum level. The SI system is based on multiples and submultiples of 10. Greek prefixes are established for multiples of 10. Mega 1,000,000, kilo 1,000, hecto 100, and deca 10, while Latin prefixes are selected for the submultiples milli 0,001, centi 0,01, and deci 0,1. Thus, a kilogram equals 1,000 grams, a millimeter equals 0,001 meter. As aforesaid, International System of Units, abbreviated SI, is used officially in all countries except in the USA, Myanmar, and Liberia. The author of this presentation strongly recommends to use always SI system of units. Using both SI and imperial system of units creates confusion and can cause errors and disasters, as will be shown some time later in 2 videos. In the imperial system, the base quantities are length with units in inches, feet, yards, and miles, time with same units as in SI, seconds, hours, days, weeks, and years, weight with unit in pound, and temperature with unit in Fahrenheit. Imperial system commonly uses weight rather than mass. Weight refers to the gravitational force on an object, whereas mass refers to the amount of matter of an object. An object has the same mass on the Moon as it does on the Earth, but it weighs less on the Moon as the gravitational force of the Moon is less than the gravitational force of the Earth. Conversions between the common units of length used in the imperial system are listed below. 12 inches is 1 foot, 3 feet is 1 yard, 1,700 yards is 1 mile. The units of time are the same in SI and imperial system. Conversions between the common units of time are listed below. 60 seconds equal 1 minute, 24 hours equal 1 day, 7 days equal 1 week, 52 weeks equal 1 year equals 365 days. Correspondence between SI and imperial units of measurement. Millimeters correspond to inches, centimeters correspond to feet, meters correspond to yards, kilometers correspond to miles. Flow rate conversion between imperial system of units and SI. Standard cubic feet per minute SCFM in imperial system of units equals 1,699 cubic meters per hour in SI system. Pressure conversion 1 pound per square inch or 1 psi equals 0,07 bar. 1 bar equals 14,5 pounds per square inch. 1 inch of water is defined as the pressure exerted by a column of water of 1 inch in height. 1 inch of water equals 248,84 Pascal. Documentation. This topic, as said, describes the documentation necessary for operation and maintenance of a plant, with the accent on instrumentation, and represents my unique contribution to make operation and maintenance understandable, affordable, and safe. There are 10 types of documentation in a process plant of project. 1. Hazardous area, which shows hazardous zones in a plant. 2. Process description describes the process. 3. Block diagram is a schematic illustration of the major process units. 4. Process flow diagram shows the relationships between the major components of a process plant. 5. Piping and instrumentation diagram is a schematic illustration of functional relationship of piping, instrumentation, and system equipment components. 6. Layout is the disposition of all equipment and instruments. 7. Instrumentation index is the list of all instruments. 8. Datasheet contains all data of an instrument. 9. Loop diagram shows all electric or pneumatic connections of an instrument. 10. Manual describes the operation, installation, and maintenance of an instrument. At the end of this topic, I have put a brief description of symbols used in various process diagrams, especially in piping and instrumentation, and loop diagrams, because every technician or engineer must be able to read process diagrams. Hazardous area is an area where the atmosphere contains explosive or flammable concentrations of gases. There are 3 zones in a hazardous area: Zone 0, Zone 1, and Zone 2. Zone 0 is where hazard is present continuously, for example in tanks with gasoline which evaporates producing explosive gases. Zone 1 is where hazard is likely to occur in a normal operation, for example around flanges. Zone 2 is where hazard is likely to occur at great distance from flanges or in case of abnormal operation. In this example of hazardous area, close to valve release is Zone 1 and more distant Zone 2. In this example of hazardous area, close to valve release is Zone 1 and more distant Zone 2. In this picture, hazardous area Zone 0 is inside tank. zone 1 around flanges, and zone 2 distant from flanges. Process description. Example of process description. Condensate storage and pumping system. The condensate product is pumped by condensate pumps to the condensate storage tanks. The two storage tanks are operated in the following manner. One tank is filling with rundown condensate product. One tank is settling for the first 8 hours and is export for the following hours. A block flow diagram BFD is a schematic illustration of the major process units. The blocks or rectangles are used to represent a unit operation. The blocks are connected by straight lines which represent the process flow streams which flow between the units. A process flow diagram PFD shows the relationships between the major components in the system. PFD also tabulates process design values for components in different operating modes, typical minimum, normal, and maximum. A process flow diagram PFD shows the relationships between the major components in the system. PFD also tabulates process design values for components in different operating modes, typical minimum, normal, and maximum. A piping and instrumentation diagram, PID, is a schematic illustration of functional relationship of piping, instrumentation, and system equipment components. Layout is the view from above of the plant. Instrumentation index is the list of instruments. Datasheet contains all instrument data. Loop diagram shows all electrical connections of an instrument. Manual describes the operation, installation, and maintenance of an instrument. Below is an example of ABB Model 266 pressure transmitter. There are many symbols used in documents, mostly in two of them, piping and instrumentation and loop diagrams. And in this lesson, we will illustrate and explain the most important of them. Documentation containing piping and instrumentation and loop diagrams begins with the legend containing the explanation of symbols. Here are some extracts of a legend. There are 4 graphical elements and or functions of a PID. Discrete instruments, DCS distributor control system functions, PLC programmable logic controller functions, and ESD emergency shutdown functions. Field mounted instruments are indicated by a circle. DCS functions are circles surrounded by a square with eventually H and L indicating high and low function of a variable. PLC programmable logic controller functions are indicated as follows. ESD emergency shutdown functions are indicated as follows. In this table, common connecting lines are represented. Instrument identification is composed of 2, 3, or 4 letters, of which the first letter always indicates the process variable measured by the instrument. L for level, T for temperature, P for pressure, F for flow. The second letter can actually be a group of letters which represent the function of the instrument. T for transmitter, I for indicator, C for controller, R for recorder. This PID example shows a so-called steam reboiler where steam heats process fluid. If, for example, process fluid temperature measured by temperature transmitter TT206 is greater than the set point temperature at controller TRC206, the controller will close the control valve TCV206 to decrease the flow of steam to reboiler. On the left, we see the real look of instrumentation and reboiler. On the right, we see the PID with TI206 temperature indicator, TT temperature transmitter with capillary tubing and pneumatic output line, TRC206 pneumatic temperature controller, and TCV206 pneumatic control valve. Explosion protection of instrumentation. Hazardous areas. Hazardous area is an area where the atmosphere contains explosive or flammable concentrations of gases. There are three zones in a hazardous area: Zone 0, Zone 1, and Zone 2. Zone 0 is where hazard is present continuously, for example in tanks with gasoline which evaporates producing explosive gases. Zone 1 is where hazard is likely to occur in a normal operation, for example around flanges. Zone 2 is where hazard is likely to occur at great distance from flanges or in case of abnormal operation. In this example of hazardous area, close to valve release is Zone 1 and more distant Zone 2. In this example of hazardous area, close to valve release is Zone 1 and more distant Zone 2. In this picture, hazardous area Zone 0 is inside tank, Zone 1 around flanges, and Zone 2 distant from flanges. Hazardous area is an area where the atmosphere contains explosive or flammable concentrations of gases. Explosion or fire can be caused by an electrical spark, arc, or temperature. Instrumentation located in a hazardous location must be designed to avoid producing sparks or heat. In process plants, there are only explosive gases that can cause an explosion. An explosion is defined as a reaction of explosive matter and oxygen in air initiated by fire in form of spark or by heat. Explosion generates fire and pressure. Fire has no pressure, and absence of pressure distinguishes it from explosion. Conditions for an explosion. For an explosion to happen, three factors have to be present at the same time: flammable gas, oxygen in the air, source of explosion, spark or heat. Three methods of explosion protection. In order to reduce the risk of explosion, eliminating one or more of the components of the explosion triangle is necessary. The three methods of explosion protection are: explosion containment, the only method that allows the explosion to occur but confines it to an enclosure, thus avoiding transmission to the surrounding atmosphere. It is called flame-proof or explosion-proof protection. Segregation, a method that separates instrumentation from the explosive mixture. Most used method is putting instrumentation under air pressure higher than surrounding atmospheric pressure, preventing explosive gases to enter pressurized enclosure or cabinet. Prevention, a method that limits the energy, electrical and thermal of field instrumentation and is called intrinsic safety. Lower explosive limit, LEL. When the concentration of gas is below the MIE, minimum ignition energy, the gas cannot explode but only burn. Upper explosive limit, UEL. When the concentration of gas is above the UEL, the gas cannot explode and burn. Combustion will only occur if the flammable mixture comprising fuel in the form of a gas or vapor and air is within certain limits. These limits are lower explosion limit LEL and upper explosive limit UEL. According to probability of occurrence of the explosive atmosphere, hazardous area is divided into Zone 0, where gases are present continuously, more than 1,000 hours per year, for example in tanks. Zone 1, where gases are present in normal operation, between 10 and 1,000 hours per year, for example around flanges. And Zone 2, where gases are present in case of abnormal situation, less than 10 hours per year. There are three groups of gases regarding their minimum spark energy to cause explosion. 2A, 180 microjoules, example propane. 2B, 60 microjoules, example ethylene. 2C, 20 microjoules, example hydrogen. There are 6 classes of gases regarding gas minimum temperature of explosion without the presence of spark. The 6 classes of temperature are referred also to the maximum operating temperature of an electrical equipment. Minimum temperature of explosion of a gas must be superior to the maximum operating temperature of an electrical equipment. Table showing from the left temperature classes, ignition or explosion temperature ranges, and maximum permissible surface temperature of electrical equipment. T6 class of a gas is the most dangerous because the gas belonging to T6 class can explode at a very low temperature. On the other hand, T6 equipment class is the best because its operating temperature is very low. A table showing various methods of explosion protection and their code. P is pressurization. D is flame-proof or explosion-proof enclosure. I is intrinsic safety, and we see also E, increased safety. Flame-proof or explosion-proof protection, marking D. This protection method is the only one based on the explosion containment concept. This method allows the energy source to come in contact with the dangerous air-gas mixture. As a result, the explosion takes place but is confined in an enclosure built to resist the excess pressure created by an internal explosion. The explosion does not propagate to the surrounding atmosphere. Electrical equipment in hazardous area uses only explosion-proof protection. Instrumentation can use this protection, but not necessarily. Intrinsic safety marking IA for zone 0 and above, and marking IB for zone 1 and above. Intrinsic safety is based on the principle of limiting the energy to come to field instrument. The electrical energy is kept below the minimum ignition energy required for each gas. The intrinsic safety level of an electrical circuit is achieved by limiting current and voltage and thus power and temperature. Therefore, intrinsic safety is limited to circuits that have relatively low levels of power. Increased safety with marking E is explosion protection of junction boxes with only cable terminals with great quality execution. Pressurization marking P. Pressurization is a protective method based on the segregation concept. This method does not allow the explosive gas to penetrate the enclosure containing electrical parts that can generate sparks or dangerous temperatures. A protective air or inert gas is kept inside the enclosure with a pressure slightly greater than the surrounding atmosphere pressure. It is used mainly for analyzer shelters. Measurement error. Instrumentation is science of measurement. It is impossible to achieve error-free measurement. There is always an inaccuracy in every measurement. A measurement error is always present. There are three definitions of measurement errors. Absolute error is the difference between exact measure M and effective or actual measure ME taken by person who carries out measurement. E abs equals M minus ME. E abs is absolute error, ME exact measure and M effective measure. Absolute error is expressed in measurement units, for example in units of flow, pressure, temperature or level. Relative error is absolute error divided by exact measure. ER is relative error. ER equals E abs divided M. As exact measure is not known, instead of it, the actual measure ME is used. So relative error is absolute error divided by actual measure. ER equals E abs divided ME. Relative error has no units of measure. It can be seen from relative error definition that relative error is big if measurement ME is small. Every instrument has a measurement range or measurement scale. The measure must never take place at the beginning of scale when measure is small and therefore relative error big. Percentage error is relative error multiplied by 100. EP equals ER multiplied 100. EP is percentage error. Percentage error must always be referred at which part of measurement range is taken. For example, percentage error of 1% must be defined that it is referred, for example, to the end of range. Instrument class is absolute error expressed as percentage of instrument range. Example, pressure gauge of range 0 to 10 bar and class 1 means that its absolute error is 1% of 10 bar, that is 0,1 bar. Relative error is absolute error divided by effective measure. ER is relative error. ER equals E abs divided ME. In our case, let us calculate relative error at the end of range at 10 bar. ER equals 0,1 divided 10 equals 0,01. EP equals ER multiplied 100%. EP is percentage error. EP equals 0,01 multiplied 100 equals 1% of measurement of 10 bar. In the middle of range at 5 bar, ER equals 0,1 divided 5 equals 0,02. Percentage error EP equals 0,02 multiplied by 100 equals 2% of measurement of 5 bar. It can be seen that measurement at the middle of range has a relative and percentage errors twice higher than at the end of range. Absolute error is always the same. Class of the instrument is absolute error of measurement expressed as percentage of instrument range. For example, if a pressure gauge has the range of 0 to 10 bar and the class of 1, its absolute error of measurement is 1% of 10 bar equals 0,1 bar. Absolute error is the same on the whole range. Relative and percentage errors are smallest at the end of range, at the greatest at the beginning of range. Measurement error in a plant can be 5% of measurement range of an instrument. Measurement error in control can be 2% of range. Measurement error in flow meters at the inputs and outputs of plants can be 1% of range for gases and 0,5% for liquids.